Modernage MCQs Physics second year, unit number 18, Dawn of Modern Physics, Part 2. The ratio of conductor length to the proper length of a meter stick is option A, L to L naught is equal to 0, option B, L to L naught less than 1, option C, L to L naught greater than 1, option D, L to L naught greater than or equal to 1. The key is L to L naught less than 1. Therefore, the correct option is B. Reason: the result of theory of relativity for length contraction is L is equal to L naught into square root 1 minus V square divided by C square, where L naught is proper length and L is contracted length, as V is less than C, which is the speed of light. Therefore, the square root 1 minus V square divided by C square is less than 1. Therefore, L is less than L naught, or L to L naught is less than 1. Hence, the ratio is L to L naught less than 1. At temperature T, the wavelength lambda m is corresponding to maximum intensity of radiation from black body. The mathematical form of Wien's displacement law is A. Lambda m plus T is equal to constant. B. Lambda m minus T is equal to constant. C. Lambda m minus T is equal to 0. Or option D. Lambda m into T is equal to constant. The key is lambda m into T is equal to constant. Therefore, the correct option is D. Reason: from the experimental data of black body radiation spectrum, we came to the conclusion that the wavelength corresponding to maximum intensity is inversely proportional to temperature. That is, lambda m is proportional to 1 by T, or lambda m is equal to constant divided by T, or lambda m into T is equal to constant. Hence, the mathematical form of Wien's displacement law is lambda m into T is equal to constant. Which one of the following can be used to determine the temperature of a star? Option A, Wien's displacement law. Option B, Steffen Boltzmann law. Option C, Planck's quantum theory. Option D, Rayleigh's theory. The key is Wien's displacement law. Therefore, the correct option is A. Reason: a definite wavelength always corresponds to a color. By measuring the wavelength lambda m from the color of star, the temperature T can be calculated by using the equation lambda m into T is equal to constant equal to 0.002898 meter Kelvin, which is Wien's displacement law. Hence, the temperature of a star is determined by the Wien's displacement law. Choose the correct formula of Steffen Boltzmann law for intensity E of radiation at temperature T. Option A, T is equal to sigma e power 4. Option B, E is equal to sigma T power 4. Option C, T is equal to sigma e power 2. Option D, E is equal to sigma T power 2. The key is E is equal to sigma T power 4. The correct option is B. Reason: the Steffen Boltzmann law is stated as the intensity of radiation is proportional to the fourth power of absolute temperature. Therefore, E is proportional to T power 4 or E is equal to sigma T power 4, where sigma is the constant of proportionality. Hence, the Steffen Boltzmann law is E is equal to sigma T power 4. The temperature T of a black body is doubled to increase the intensity E. Option A, 60 times E. Option B, 8 times E. Option C, 4 times E. Option D, 2 times E. The key is 16 times E. Therefore, correct option is A. Reason: the Steffen Boltzmann law is E is equal to sigma T power 4. Therefore, E prime is equal to sigma T prime power 4. And E prime is equal to sigma into 2T all power 4, because the temperature is doubled, which is equal to 16 into sigma T power 4, because 2 power 4 is equal to 16, which is equal to 16 times E, because E is equal to sigma T power 4. Hence, the intensity increases from E to 16E. The photoelectric effect can be explained on the basis of option A, the wave nature of light; option B, the particle nature of light; option C, wave particle nature of light; option D, magnetic field vibration of light. The key is the particle nature of light. Therefore, the correct option is B. Reason: the instantaneous emission, the frequency dependence emission, and energy of photoelectrons was not explained by wave nature of light. Einstein explained these results by extending Planck concepts of quantization to light. Hence, the particle nature of light explains the photoelectric effect. What does happen to the kinetic energy of photoelectrons if experimenter increases the intensity of radiations? Option A, decreases; option B, increases; option C, not change; option D, becomes 0. The key is not change. Therefore, the correct option is C. Reason: the kinetic energy of a photoelectron depends upon the frequency, as shown by kinetic energy is equal to hf minus phi. It does not depend on the intensity of radiations. Therefore, kinetic energy of photoelectrons does not change by increasing the intensity of radiation. Hence, the kinetic energy does not change. What is the kinetic energy of a photoelectron if the frequency of light falling on photoemissive plate is doubled? Option A, 1/4; option B, 1/2; option C, constant; option D, double. The key is double. Therefore, the correct option is D. Reason: the kinetic energy of photoelectron is kinetic energy is equal to hf minus phi. In the equation, phi is equal to hf naught is a constant, where f naught is the threshold frequency and h is the Planck constant. It depends on the nature of photoemissive plate. The kinetic energy is proportional to f, the frequency of the photon falling on the emissive plate. Therefore, the kinetic energy is doubled if the frequency is doubled. Hence, the kinetic energy of photoelectron is also doubled. The maximum kinetic energy of a photoelectron depends on Option A, frequency of incident light. Option B, intensity of incident light. Option C, wavelength of incident light. Option D, temperature of metal plate. The key is frequency of incident light. Therefore, the correct option is A. Reason: the kinetic energy of a photoelectron is kinetic energy Ke is equal to Hf minus phi. In the equation, phi is equal to Hf naught is a constant. It depends on the nature of photoemissive plate. Therefore, kinetic energy is proportional to F. Hence, the maximum kinetic energy of photoelectron depends on the frequency of the incident light. The rate of emission of photoelectrons from a metal surface depends on option A, frequency of incident light, option B, intensity of incident light, option C, wavelength of incident light, option D, temperature of metal plate. The key is intensity of incident light. Therefore, the correct option is B. Reason: the intensity of light is proportional to the number of photons. Every photon of frequency greater than threshold frequency of the metal can emit electron. Hence, the rate of emission of photoelectrons depends on the intensity of incident light. What is the uncertainty in energy of electron of hydrogen atom in ground state? Option A, delta E is equal to 0 joules. Option B, delta E is equal to 6.63 joules. Option C, delta E is equal to 6.67 joules. Option D, delta E is equal to 9.11 joules. The key is delta E is equal to 0 joules. Therefore, the correct option is A. Reason: according to uncertainty principle, or the uncertainty in the energy is delta E into delta T is nearly H, or where H is the constant known as Planck constant, or the uncertainty in the energy is delta E is equal to I divided by delta T. Under normal conditions, the electrons of hydrogen atom remains in ground state for longer time. Therefore, the uncertainty in time delta T tends to infinity. Therefore, delta E is equal to I divided by infinity, which is equal to 0 joule. Hence, the uncertainty in energy of electron in ground state is 0 joules.